All right, so today we'll be learning about machine learning, and this whole course is put together by the Geospatial Hub. All right, so before we dive in into learning about machine learning, I feel it's just important for us to know a little bit about the hub. So basically, the Geospatial Hub it's basically a hub to connect people together, and not just connecting people together. Beyond connecting people together, we observed a learning and we observed the knowledge and skill gap in what the institutions in Africa are like teaching the students, and what the workspace actually requires. So we thought about bridging this gap, and we created the hub. So our vision is basically to create a nurturing community for geospatial professionals. And how we go about this is to provide geoprofessionals with easily accessible skills and knowledge to meet up with international standards. So we'd also appreciate it if you follow us on all of our social platforms. So on YouTube, on Instagram, Twitter, and Facebook. So you can always follow us, and we maintain the same name across all platforms. So you can just search the Geospatial Hub. So to meet our mission, we've been using YouTube, and we basically do this kind of webinars monthly. And aside monthly, we also upload weekly videos on YouTube to cover different aspects of geospatial. So on YouTube, you can go to YouTube and search the Geospatial Hub. So once you search the Geospatial Hub, our channel will come up, and if you go to our playlist, you'll see different videos we've done in the past. So last last month we did something regarding Python. So if you want to learn Python, if you are new to Python, you could always so if you want to learn Python, you could always come to our playlist and watch what we have here. And we have like quick hacks on stuff you can like easily do, like how to do stuff easily. So you could come to this as well to see how you could like easily get stuff started with. And also we have a playlist for remote sensing. So the remote sensing, we cover Google Earth Engine, and we cover the basics of remote sensing. We have, if you are new to Geospatial, you could also um, watch this playlist. It's just basically the know-how of GIS, and also if you want to get started with GIS, you could also start with this particular playlist, GIS ArcMap. So basically, we have a whole lot of content just ready for you to consume on our YouTube channel. So kindly do well to follow us on our YouTube, the Geospatial on YouTube, and also um, it would be nice if you as well follow us on our social media. We basically post a lot on our social media. So once again, the Geospatial Hub on all platforms, and I would like to announce to us that we are launching our website soon. So on the 9th of September, we'll be launching our website. So during our past webinars, we've been getting people asking us questions that can I get certifications for the courses we are doing, and just to incorporate a whole lot of stuff together that we cannot achieve on YouTube, like blogging and all of the stuff. So we just thought about putting up a website where you can actually like go there and get all these webinars, and also get different courses. And if you want to read about Geospatial, you could also go to the blog, and it's a whole lot to explore. So we're launching soon, and would send to your mails once we launch. All right, so about me, this is me. My research interest is in disaster response, and also monitoring crop health with remote sensing. I've been doing that for about 2 to 3 years now. And also for my background, I studied surveying and geoinformatics in Obafemi Awolowo University in Nigeria. And if you want to contact me, you can reach out to me on Twitter, on LinkedIn. On LinkedIn, I'm Aremo David. On Twitter, I'm at Dave_Vid. And also, you can also shoot me a mail. My email is aremodavid20@gmail.com. All right, so we'll get started properly with the class. But before we get started, I want to show us what the form looks like. So we had the number of responses, with the form, and for how people will rate their Python knowledge, because we'll be using Python a lot in day two of this course. The day two is tomorrow. So about 40% of those people that signed up are beginners Python, and two about 21% have 2% have a scale of 2, and from a scale of 1 to 5, 40% choose 1, 2 choose 21, and 3 choose 22. So I'm a little bit concerned about people that have just the beginners that just have very very basic knowledge or no knowledge at all. So like I mentioned, last month our webinar was basically um, about Python. So if you're a beginner, kindly go to our YouTube channel and watch this Python walkthrough. It will really prove good for you. Just let me put it that way. You would really enjoy the content, and so once you watch that, it will be handy. So tomorrow's class, you won't be like lagging behind. So if you have time, you might just do, because we'll be using a lot of pandas. So if you have time, tomorrow we might do a quick review of pandas before we continue. Basically for the people with like the beginners knowledge. All right. So if you're just joining us, we've been talking about the hub and also myself and what we'll be learning today. So we just move forward. So this session is a 2-day session, and we'll be learning the basics of statistics, because before we can build any machine learning model, we have to understand statistics. Like statistics is like the bedrock for machine learning. So I don't know how much time would consume at the long run, but the classes are we are trying to like make the class maximum of an hour, 30 minutes. So depending on how we flow today, how fast we are today, we might move into day two activity, and if we are still on day one, then we'll have to like stop once it's about an hour, 30 minutes to permit people ask questions. Then tomorrow we'll pick it up from there. But day two is pretty short, because day two is coding, and today is just about explaining concepts of machine learning and stuff like that. But the coding part is just running lines of code, and actually like uh, it's actually without effort. So for further webinars, would appreciate it if you join the webinar with the mail you signed up with. If you do that, I won't have to always like go to admit the invitees. Would really appreciate that. All right, so today we'll start with statistics, and let's just get started. So what is statistics basically? So from I was trying to get like different resources, and try to. So the aim of this course is to, or the aim of this webinar is to break down every concept of machine learning to a 5-year-old. So we are not trying to explain things that are like pretty difficult or vague. So you might be seeing definitions that are just one line or just 2 lines. So we are trying to make it as simple as possible. So this is one of the easiest explanation of statistics I saw. So I just thought I should give you the definition from Wikipedia. So statistics is a discipline that is concerned with collection, organization, analysis, interpretation, and presentation of data. So now, if you look at all of this, statistics is basically concerned about data. Everything we do in statistics is about data. So our data is like very important to statistics, because we collect this data, we organize this data, we analyze this data, and we interpret, and finally we present this data. So we need to learn, if we want to like learn about statistics and machine learning. I mean, even the whole umbrella name is called data science. So it's always about data. So if we want to, we have to have like a very fundamental knowledge about data. So we'll be diving deep into data basically. So for data, we basically have two types of data. We have the sorry right. Sorry about that. That was the wrong slide. All right. So for data, basically, we have two types of data. We have the uh, qualitative data, and it is also called the categorical data. So we are trying to qualify something. And now the other type of data is the quantitative data, which is the numeric data. So we are trying to quantify something. So for the qualitative data, we cannot represent it with numbers. It cannot be represented with numbers. But for the for the quantitative data, which is the numeric data, we can represent them with numbers. So for qualitative, we have the ordered data, and we have the one that is not ordered. So the ordered data is called the ordinal, and the one that is not ordered is basically called nominal. So nominal is trying to talk about how you categorize stuff, maybe your name or something. Now for the ordinal, it's trying to prioritize something. So for example, say you're trying to give a review about your mom's meal. So you can say your mom's meal is like very spicy, it's not spicy, or it's moderately spicy. So you're trying to order it. So that's, but you cannot assign a number to it. So that is the qualitative. And now when you come to the quantitative, we have discrete and we have continuous. So for discrete, discrete are basically whole numbers. Say how many people are attending this class right now. Then the continuous are basically numbers that vary within a range. So it could be fractional. Say for example, the value, I like using the value of pi. Pi is 3.14 and a lot of other digits behind it. So it's like kind of a continuous data. So just to this is what I just gave now is a brief overview. So let us just go like into it in more details. So now, like I mentioned earlier, we have two types of data, and I also explained that statistics is basically revolving around this data. So we need to have a good understanding about this data and able to like process it and also get information out of it. So we have two types of data. We have the quantitative data and we have the qualitative data. Remember, the quantitative data can also be called the numeric data, and the qualitative data are the categorical data sets. So now, if you want to distinguish between these two types of data, the easiest way to go about distinguishing them is that the quantitative data, you can assign numbers to them, you can assign values to them, you can give them numerical numbers, but and that is why it's called numeric data. But the qualitative data, we cannot do this. So that's why we call them categorical. So that is one way to like highlight the differences between numeric and categorical data. So I might use them interchangeably, but just have it at the back of your mind that whenever I'm talking about numeric data sets, I'm talking about the quantitative, and whenever I'm talking about categorical, I'm talking about the qualitative data sets. So for quantitative data, which is also the numeric data, like I mentioned, it can be measured numerically. So we can also split this type of data into two smaller chunks, and that is the discrete data and the continuous. So when we talk about discrete data, we are talking about numeric data in whole forms. They are countable. For example, right. So at the moment of this recording, we have about 43 people in this class. So if we are trying to like qualify this data, we can say this is a numeric data and it's a discrete data because we can count how many people we have, and from the total we have 43 number. We have 43 people at the moment in this class. So another example of discrete data could be how many languages do you speak. So for me, I speak Yoruba and I speak English like very well, and I'm learning Spanish. So I can say three. So I speak three languages. So it is discrete. We can count them just 1, 2, and 3. It is discrete. But now the other type of quantitative data we have is the continuous data. So now these continuous data, they are also numeric data sets, and they're in fractional forms. So it can assume any value over a certain interval. For example, your height. So for me, I'm about 1.7. I'm about 1.7, I think, 4 meters. So this data, it is not discrete, it is continuous because it is over a range, because that is not the absolute value. Like 1.74 is not like the absolute value, it's about 1.74, then some other digits behind it, so it is continuous because it isn't discrete. You can't just like pin it that, oh, if it's that I would say 1 meter and I was 1.0 meter, then it is a discrete data. But I can't be 1.0 meter, I can just be 1.74321, and just have a lot of continuous information. So I like using pi, like I mentioned earlier. I like using pi for continuous data because if you check the value of pi like is 3.142 and all other um, digits behind it. So if you want to get more information about the differences between discrete and continuous data, I gave this link. So if you click this link, it has a whole lot of other information about discrete and continuous data. So I'll just copy this link and I'll paste it. I'll paste it in the chat box. So if you want to read more about discrete and continuous data sets, you can always go to this particular link I just shared. Yes, this session is being recorded, and we'll be uploading them on our YouTube channel. So I hope we have like a basic knowledge of the qualitative or the categorical data sets. So now we'll move on to, sorry, we just spoke about quantitative and numeric. So now we'll move on to qualitative, and qualitative data sets are also called categorical data. So like we explained previously, we cannot assign numerical values to qualitative data. That is why it's called qualitative. We are trying to qualify something. For the quantitative, we are trying to quantify something. So if we are quantifying, we like give it a number. And also for the qualitative, if you are qualifying, you don't give it a number. You just qualify it with something. For example, like I explained, how spicy a is a particular food. Is it very spicy? Is it not spicy? Or is it mildly spicy? So now for qualitative data, we have two types. We can break them further into two types. We have the nominal and we have the ordinal. So the nominal, like I mentioned earlier, they are not ordered. They're not ordered. So they're just like names of like your name or labels, or maybe your country name. I'm from Nigeria. Like earlier in the call, we had people from Uganda, Ghana. So all these are like qualitative data sets, but they are under the nominal because they are like names of places, they are like labels we're trying to assign to our data set. Then also we have ordinal. So ordinal is, we cannot assign a value to it, right? But it is ranked, it is ordered. So for example, the t-shirt I'm wearing, what is my size? So I prefer wearing extra large. So you can like rank them in large, extra large, extra large, and stuff like that. Then your satisfaction score, say at the end of this class, we'll be given another Google form to fill about like feedback, just to get a feedback about the class. So if you're satisfied about the class, you can just pick satisfied and not. So these are ranked data set. They are ordered, right? You cannot assign a value to them, but um, you can they are ranked basically, but we are not assigning numeric values to them. So that is like an overview of the two types of data we have. So we have the categorical data and we have the numeric data, which we've like discussed extensively. And now we'll move on to the type of statistics. So all of these data, right, we can get more information about them and we group them under type of statistics. So we have two types of statistics. We have the descriptive statistics and the inferential statistics. So now for descriptive statistics, you are trying to describe our data sets, right? We are trying to like describe our data sets, probably with mean, median, mode, range, or variance. We're just trying to get more information, like more info about our data sets. So that is for descriptive statistics. And when it comes to inferential, we are trying to inference. We are trying to make inferences based on something. What will happen if I increase this, with this decrease, with this increase? So we are trying to make assumptions. We're trying to predict. So basically, that's just what descriptive and inferential statistics is about. So let's just talk a little bit more about them. So descriptive statistics is basically trying to describe our data using tables, using graphs, and summary measures. So for the for descriptive statistics, these are like the four tools we use. The measure of central tendency. So for measuring central tendency, we use mean, median, mode. So central tendency is just like it's trying to check our data sets, right? So we have this data. For example, while we're collecting information about this class, we ask for age and we ask for number of hours you sleep. So now, let's say for age, for example, we are trying to see the age group of this class. What is like the central tendency? It means what is that value that is in between. You understand? So that would be like the measure of the central tendency. So we are trying to look at values that are like recurring the most, or values that are in between or something. So that is basically central tendency. Then we have measure of dispersion. So the measure of dispersion is trying to explain how far apart are these data sets. So we have data of people that sleep. So if we have people, let's say the average sleep time is 6 hours, and we have someone sleeping for 10 hours, then we know there's like probably there's this dispersion there. So we're trying to see how the spread basically, yeah, that's the word. So measure of dispersion is basically trying to like talk about the spread of the data. Then we have the frequency distribution and we have the histogram. So that is just a quick overview of descriptive statistics. And now inferential. So inferential, like I explained earlier, is used to make inferences from our data. So it consists of method um, that helps us to make decisions or prediction about a population. So we have the ANOVA, we have the linear regression, we have decision trees, and we have others. So for this particular course, we just focus on the linear regression, and more precisely simple linear regression. All right, so we spoke about this descriptive statistics earlier, and now we just try to understand it more in detail. So we might be doing a little bit of maths. If you're not comfortable with maths, don't worry, we'll try to make it as simple as possible, so we won't do anything overly difficult. All right, so the first is the measure of central tendency, like I explained earlier. So the first way we measure centers is using mean. So basically, mean is just getting the average. And I have this here. I use the data set to illustrate, so I don't forget to illustrate. So I don't forget to illustrate what mean means mathematically. So now we have two different types of mean. We have the mean for population, and we have sample mean. So the basic difference is, let me just, instead of telling you, let me just show you. So from the data we collected, all right, so this is what the responses looks like from the data we collected. So I removed people's email address and their last name. So this is what the data we collected looks like. So I cleaned this data a little bit because the data wasn't really cleaned. So but that will be another whole course, cleaning data and stuff like that. So now we have age. So you could see some values are missing. We'll talk about how to treat all of these missing values tomorrow. So now look at this. Now we have age. We have different numbers for the age. So now say we want to get the mean. So okay, now before I go to the mean, I want to explain what population is and what sample is. So now if I get the mean for this entire sheet, that will be the population mean of this particular data set. But instead of taking the population, now for example, we have about 8 billion people worldwide. So you could actually, if you get data about everybody in the world and you want to like uh, make some statistical model. So now that data you get is the data for the population. But now when you get a subset of that data set, then it is called sample. So now instead of getting the mean for this entire population, we just get maybe the first six. So the first six, so we can just get the mean for the first six. So now once we get the mean for the first six, then it is called sample mean. So I hope that is like clear. So now to get mean, so mean is basically the summation of all the values divided by the numbers of our data. So to do that, what we have to do now, so we'll be working with sample throughout the entire class. We'll be using the entire population just like save time. So now this is the first six. This is the first six values, right? So now to get the mean of these first six values, we can just Excel makes it easy for us to use formulas to do that, but I don't want to use formulas. So what we can do is to just say we add all of these values: 21 plus 8 plus 25 plus 24 plus 26 plus 22. Then we divide this by 6. Then we get our mean. So that is how to get mean. But because of our time, I'll just use the formulas. So on Excel, if you want to get the formula, you just start with an equals to, then you so for mean, the keyword for mean is average. So now once you press average, now you select all the columns you want to work with. So I'm working with just the first six columns. Now you close the bracket and you press enter. So the mean age for this population, for this sample rather, sorry, the mean age for this sample is about 24.3. And if I got the entire age, if I do for the entire Excel sheet, then it is population mean. So I just want us to like differentiate early on the difference between population mean and sample mean. So what I did here is sample mean. All right, so that is how we measure centers mean. So the next thing is median. So basically, the median is the middle value of a data set when the data has been ordered. So by ordered, we could arrange the data set ascending, we could arrange the data set descending. All we just have to do is to order the data set, and once we order the data set, the middle value is the median. So now for median, if the number of observation is odd, then the median is given by the middle value, right? So you can only have one middle value. But some cases you have even numbers of observation. So when you have even numbers of observation, so what you do is you take both values in the middle, then you divide it by 2, then you get the median. So let's say for our data set as well, if you want to get the median, so let me just label this as mean. So now, if you want to get the median, so Excel gives us the same formula to like Excel gives us formulas to work with medians. So you can just say equals to, then you have median. So now, if I press this median and I also give it the range of values I want, it basically does everything automatically, and it gives us the median. So now, like I mentioned earlier, if if the data set is even, so for even data sets, it averages it. So that is what it has done here. So we have just an even number here. So it averaged by even number, I mean we have even numbers of values in our data set. This is 1, 2, 3, 4, 5, and 6. So it averaged the two values in the middle after arranging it from ascending, um, after arranging it in an ascending order, then it got the median value. So median is basically the middle number. So next up we have the mode. So basically, mode is the highest occurring number in any given data set. So the mode, when we have a data set and we have two numbers that are occurring very frequently or more frequently, then we say that particular data set is bimodal, meaning it has two modes. And when it has more than two modes, we say the particular data set is multimodal. And when it doesn't have node, we just say the data set does not have mode. So basically, that is a brief overview of measures of centers. Now, we want to see the relationship. How does mean, median, and mode? How does these three data sets relate with each other? So this is so the image we have here is trying to show the relationship between mean, median, and mode. So I want to talk about, okay, so I'll talk about that later. So now the diagram we have here shows the relationship between the mean, the median, and the mode. So when the mean, median, and mode, when they are actually the same thing. So if you have, like, let me say perfect in quotes, when we have a perfect data set, so that means the mean, median, and mode are the same value. So for a perfect data set, the mean, median, and mode are the same value. And when we try to like plot it, it gives us this symmetrical plot where the mean, median, and mode have the same value. But excuse me, please. But when we talk about real world data sets, it is very um unlikely for our mean, median, and mode to be the same value. So in our real world data sets, we have outliers. For example, if you look at the data sets we collected, if you look at this, we have missing values. If we input the missing value, um, it might change the way the the graph looks like. I think for the sleep, somebody indicated 1 hour. I'm not sure. But while I was going through the data set, I saw someone indicates 1 hour. Probably okay, that's for age. Someone indicated 1 hour. So now this person is saying is 1 year old. So those type of values, right? Values that are too small or too large, or values that look different from the group of data sets we have. Those values are actually called outliers. So when we have outliers, it kind of skews our data sets. But even regardless of the outlier, our median remains in the middle. So our median remains in the middle. So now this effect of outlier either causes the mean, that's the like central tendency, like the mean, the average of the data set to be skewed to the left or to the right. So now um mean is highly influenced by outliers. So from the image we have on the right, the far right, we have the mean of this data sets being influenced by an outlier. So for outliers, we'll learn how to deal with outliers tomorrow. So we can either remove outliers, we can either cap outliers, we can floor outliers. So tomorrow will be basically about coding. So we'll talk about all of this. So now one very important thing to note here is that the node. So for mode rather, we can calculate mode for both uh, qualitative and quantitative data, and that is the edge mode has over median and mean. So in some cases, depending on our particular data set and depending on the business knowledge, we we um, we feel missing values with mode, like the highest occurring number, because we can also get mode for both qualitative data sets and quantitative data sets. For example, I was explaining about spiciness of food. Is the food mildly spiced? And that is when we are talking about qualitative. So you can actually get how many people or if you give a form to talk about the satisfaction level of this class, so you can actually get how many people picked satisfied, how many people picked not satisfied. Now we can get what is the most picked value. So for mode, we can get it for both qualitative and quantitative data. But when it comes to mean and median, we cannot get the mean of people that are satisfied. We cannot get it's just it is a qualitative data, so we cannot get the mean of qualitative data. We can only quantify something to get the mean, and that is like the numeric data set. So I'm just trying to explain that mode has that edge because we can get both um, we can get the qualitative, we can get mode for qualitative and quantitative data sets. So now we've spoken about measures of sensors. Now we want to talk about measures of dispersion. All right. So for measures of dispersion, like I explained earlier, measures of dispersion just tells us about the spread of the data. How far apart are these data sets? So we'll be using range, standard deviation, and variance. So basically, when we talk about range is just the difference between the highest and lowest value in a data set. And now range is highly influenced by outliers. So range is not very useful. Like we don't really use range when we are like dealing with our data sets. So let's just give random numbers. So um, if you have say we have 1 to 10. All right, so let's say we have 1 to 10. So comment please. 1, 2. All right, so let's say we have 1 to 20, for example. All right, so these are our numbers, 1 to 20. All right, so now we want to get the range of this data set. So to get the range of this data set, it is just the highest value, which is 20, minus the lowest value, which is 1. So the range of this data set is 19, right? So now let's imagine we have another part. Let's imagine we have one more value to this data set, and the value is 100. Now 1 to 100, right? Those are our data sets. 1 to 20, then 100 rather. So now if you are getting the range of this particular data set, then it will be 100 minus 1. So now the new range will be 99. So this is just trying to explain that range is not a good it's not a valid way to measure dispersion, to measure the spread of our data, because basically this data set, the spread is just 19, and now because we have an outlier of 100, now the range is telling us 99. So basically what I'm trying to explain is that is not range is not a good measure to measure range is not a good validator to measure the spread of our data. So instead of using range, we use stuff like variance and standard deviation. So when we talk about variance, so variance is trying to um, variance is the average of the square differences from the mean. So we have different values of the mean. So let me just explain that with this. So the beautiful thing about Excel is that Excel gives us that ability to do all of this without computing. So if I want to get variance, I could just use the formula and say variance. So now you see this variance with P and you see this variance with S. So if I want to do the variance, I'll just use the one with S because I want to like do the variance for a particular sample. I don't want for the entire population. So if I click the sample we're using since, and I do this, it just gives us the variance. So now this particular figure, it is the average value that each of these value vary from the mean, which is this. So variance is the average square difference from the mean. So to get variance mathematically, what you do is that you take the particular value. So mathematically to get variance, what you do is you take this particular value, you say 21 minus the mean, then you square it. So you do the same thing, you add it to 28 minus the mean, you square it. So once you do the summation of everything, it gives you the variance, right? So that is how we calculate variance mathematically. Now standard deviation is the square root of variance, right? So this is standard deviation is represented by sigma. So sigma square is equals to this particular value. So standard deviation is the square root of variance. Now, when we are dealing with population variance, we just use the entire number of the population. But when we are dealing with sample variance, we minus one um, from the variance. So now, when we to just get more about what standard deviation is doing to our to our data sets. So larger values of sigma, it indicates that the data is more widely spread from the mean. So now if we just going back to Excel, if we do our standard deviation, so we just say equals to, then you use this standard deviation. So now we are using the standard deviation of the sample, so we pick this one with S. So now standard deviation of sample, so we pick our data set again, and once we do this, so now this is trying to tell us how this data is like spread, the spread from the mean. That is what that is saying. So if you have if this value is say larger, if this value is larger, then it means our data set is more away, it departs more, let me use the word, from the mean. So basically that is what variance and standard deviation is about. I hope we have fundamental knowledge of what we've been discussing so far. So far we've been talking about how we measure centers. We've also talked about how we measure dispersion, and now we would move into machine learning. So before we go into machine learning properly, I would just like to ask, do we so far understand what we've discussed? So if you have probably question regarding statistics. So far we've just discussed statistics. So if you have questions regarding statistics, I think you can ask now before we go into machine learning. Please go ahead. Basic. Okay, go ahead. All right. So thank you for the question. I don't know much about seismic. I don't know, like, I can't give a proper answer because I don't know the type of data you get. But regardless of the type of data you get, um variance and standard deviation are trying to measure dispersion, right? So it is trying to tell you how dispersed these values you have are from the mean. That is basically, I don't know your objective with the seismic data you have, but regardless of the type of data you have, it might not be seismic, it might be data about people, it might be data about how people are sleeping well or people are not sleeping well, it might be data about how your organization is profiting or losing money. So you can just get and also when we get to machine learning, we'll be talking about business knowledge. So business knowledge is basically trying to understand the problem, right? So now once we understand the business knowledge of things, then we'll be able to like use that to infer on what we really need to do. So basically, the variance and the standard deviation are just a means to measure how widespread um, our data sets are from the mean. I hope that is clear. So I'll just entertain one more question before we move into machine learning. All right, so I would assume there are no like further questions, so we can like move into machine learning. All right, so like I mentioned earlier, we're trying to make it very brief and very short. So in cases where you're like a beginner, you can actually get get it without get what we are trying to explain without having to use like very vague examples and stuff like that. So like I said again, we just given about just one line definitions to make things easy for us. So in the most basic term, machine learning is the practice of programming computers to learn from data. So once the computers learn from this data, now the computers can make reasonable decisions about this data, and the computer can also predict or infer about this data. So for machine learning, we have two types of machine learning. We have the supervised and we have the unsupervised learning. So we'll be focusing more on the supervised learning in this class. So for supervised learning, we have we can further break down supervised learning into two categories, which are which is regression and classification. So a lot of people do not necessarily know how to like distinguish between regression and classification. So if you want to know how to distinguish between these two, I made a tweet. I tweet basically about machine learning, GIS, remote sensing, and Python. So I'm programming basically. So if you want to learn more about this these unique differences, you can. I'll just paste this particular link in the chat box, so you can like go through it and read about it. You get more information. You get more information about the data sets. Sorry, you get more information about distinguishing between regression and classification. All right, so if there's any need for that, we might eventually revisit this particular link. All right, so like I said earlier, for machine learning, we can classify them into two classes. We have the supervised learning and we have the unsupervised learning. For the supervised learning, we can also classify it into regression and classification. So we'll be talking about regression and classification. We'll be focusing more on regression in this class. Then further classes, we can talk about classification and other form of machine learning. So now for regression, basically in regression, we're trying to remember machine learning. What we have to do with machine learning is we feed our model, like I explained earlier, we feed our model with some values, or we feed our computer with some values. Now, with these values we fed our computer with, our computer can make predictions based on these values. Now, for regression, in regression, we are trying to predict values within a continuous range. So all of this, right, we are trying to we first started with statistics so we can like build a foundation for machine learning. So now you can see what we did in statistics is kind of showing here now, like the very first thing we're doing in machine learning, we started with statistics. So now in regression we're trying to predict. So for example, for regression we're trying to predict a particular result within a continuous output. So we are not trying to predict within a discrete output. So remember we spoke about um, numeric data types, and when we spoke about numeric data type, we said some are continuous, some are discrete. So now for regression, we are trying to predict values within a continuous output. So what it basically means that we are trying to map some input variable to some continuous function. So we have this input variable x. So we are trying to map this input variable x to some continuous function. So the input variable x could be anything basically. It could be anything we are trying to predict, right? So it could be variables we are trying to like infer decisions on. So now this continuous function, mathematically, oh wow, thank you for that. I didn't notice. I didn't notice my screen share stopped. All right, so before my screen stopped, did we get this particular slide, introduction to machine learning? All right, I'll just start from here. I'm very sorry about that. I really thought my screen was still sharing. All right, so like I mentioned earlier, we're just basically trying to simplify the whole process of machine learning. So we'll be given like very simple definitions. So in simple terms, machine learning is the practice of programming computers to learn from our data sets. And once these computers have learned from our data sets, so once it learns from the data set, it kind of makes reasonable decisions about the data it has about the data it has learned from. So the decision could be probably to infer something or to predict something. So we have two types of machine learning. We have the supervised machine learning and we have the unsupervised machine learning. So for this class, we'll be focusing more on the supervised machine learning. All right, so now for the supervised machine learning as well, we can further classify it into two different classes. So we have regression and we have classification. So I was talking about some people. So if you say machine learning problem, right, you should be able to immediately distinguish, okay, this problem is a regression problem, this problem is a classification problem. So how can you immediately distinguish between regression and classification problems? So I made a tweet about it, and um, this is the link to the tweet which I posted in chat box earlier, so you can like go through it and you would have an understanding of how to distinguish between classification and regression. But let's just move on with the class. I said if we have time, we might come back to this particular tweet. All right, so now we are talking about regression, right? Remember, for supervised learning, we'll be talking about regression and classification. So now coming to regression. So in regression, we are basically trying to predict results within a continuous output, right? So this is where I was talking about. This is where I was trying to link what we've done previously. So previously we spoke about numerical data sets, and now we said for numerical, that is the quantitative data, we can actually split them into discrete data sets and continuous data sets. So now in regression, we are not concerned about that discrete data set. We are concerned about the continuous data set. So we are trying to predict values within a continuous range, not just so discrete is something like white or black, blue or red, 1 or 2, 0 or 1. So no, we are not trying to do that in regression. What we're trying to do is that we're trying to predict values within a continuous output. Sorry, pardon me. I want to mute a little bit. I have some background noise. All right, sorry about that. I just needed to attend to the background noise and make sure we're not being disturbed. Sorry about that. All right. So now in regression, we're trying to predict within a continuous range. So basically, in simple terms, we're trying to map input variable to some continuous function. So we're trying to map some input variables to some continuous function. So mathematically, the function we are trying to pass this input variable to is written as y is equals to beta naught plus beta 1x. So we'll talk about all of this very soon in more details. So I just want to show you the equation, what the equation looks like before we start talking about them. So these two are called coefficients. In some textbooks or some tutorials, you might see people call them parameters. You can see people call them model parameters or model coefficients. But what is important to know is that this beta naught is the intercept, and this beta 1 is the slope. So for example, if we are given if we have data sets about houses, we can predict the price of the particular house probably within room number of say if a particular house has this amount of room numbers, how much will the house go for? So now the input variable there, that x, this x, right, would be the room number. So if you want to write this formula, the formula will be y is equals to like this beta naught plus beta 1. Now instead of x, we replace x with room number. So basically that is the continuous function we're trying to map input variable to. So now it is also noteworthy to understand that this x is called the independent variable because, and y is called the dependent variable because we are trying to predict based on x. So y is basically dependent on x. X is actually an independent variable. So what I'm saying might be vague right now, but once we dive into the class, we would understand. So this is just like the first thing we are talking about, the first slide on regression. So it's fine if you don't understand what I'm saying. Very soon you would have a better understanding of everything I'm saying. So now that is for regression. Remember we said for supervised learning, we have regression and we have classification. So now for regression, we are trying to predict values within a continuous range. So for example, if you have a house, how much will the house sell, right? So it is like a continuous range. The house could sell for any amount. It would sell for any amount basically. So the range is actually very, very continuous. But now for classification, in classification, we are not concerned about a continuous range. We're just concerned about a discrete range, right? Like the output is just discrete. So for classification, so instead of trying to predict results in a continuous range, we are predicting output in a discrete range. So for example, here I have we are trying to classify people with or without malignant or benign breast cancer. So we have sizes of the tumor. So we have sizes of tumor ranging from 2, 5, 1, 7, and the diagnosis being for 2, it means it is benign. That means it is not cancerous. For 5, for tumor size of 5, it means it is cancerous. For tumor size of 1, it means it is not cancerous, and for tumor size of 7, it means it's cancerous. So now this is the output we are trying to get predictions from. So if you look at this output, the range is between 0 and 1. You don't have like 0, 1, 2, 3, 4, 5 till like infinity. It is not continuous. It is discrete, right? So that is classification. Classification, we are trying to like predict values within a discrete range. So now if you look at this, if you plot this, now look at this, if you plot this, you have the values ranging from 0 to 1, just 0 to 1, nothing else, 0 to 1. So now the blue showing that, oh, the tumor is not cancerous, and one showing that the tumor is actually cancerous, depending on the size. So basically, that's just a quick overview um, of regression and classification. We'll go into more details into regression very soon. So again, remember, if you want to get the differences and you want to understand if you see a problem, how would you be able to distinguish between regression and classification? Would this problem be a regression problem or would it be a classification problem? Just go through this tweet. Let me just drop the link to the tweet one more time. So um, if you want to go through the tweets, and that's my Twitter account. All right, so now we'll go into regression properly. And so if everything I've been saying has been vague, you don't really understand, you would have a proper understanding of regression after the following slides. So we've spoken about regression and classification. So a way to differentiate between regression and classification. So regression, it basically predicts a number from an infinitely many possible outcomes. For example, you want to predict the price of an house. The house could be any figure. It could be any figure. But classification, it predicts categories from a small number of possible outputs. So this, with the size of this tumor, is it cancerous? Is not cancerous? Just two classes. So that is the way to like easily differentiate between regression and classification. So now for unsupervised learning, so unsupervised learning, it is from the name, it is unsupervised. We are not like we're not implicitly we're not telling the computer this is what to do. So the computer basically, I'm glad a lot of us have geospatial background. So now when we are doing GIS, or sorry, when we are doing remote sensing and we are trying to do land use, land cover, we could do supervised and unsupervised. So remember, when we are doing unsupervised, we don't train our classes. By classes, I mean land cover classes. We don't tell the computer this is vegetation. We don't tell the computer this is water. We don't tell the computer this is built up or urban. We just give the computer the image, and giving that computer when we give the computer the image, it basically outputs different classes for us. So it outputs vegetation automatically by itself. So we don't explicitly train the computer to like say this is a particular land cover class. So it uses clustering. So it clusters, say, pixels that have like the same digital number, similar digital numbers, and it makes a group out of it. So unsupervised learning is just trying um to predict without like explicitly telling it to like without training explicitly. So the algorithms for unsupervised, this is not exhaustive. This is just like the few I did for my research. So clustering and every other one we have here. So we won't be talking about unsupervised learning. We'll be basically focusing on supervised learning. So now, like I said, we'll be focusing on supervised learning and we're focusing on linear regression, and we'll streamline it down to simple linear regression or simply regression. So now, for linear regression, so remember earlier we spoke about regression. We just gave like a brief overview of regression. So now we are going deep into regression. So for linear regression or regression simply, basically what we are trying to do is that we are attempting to model the relationship between a dependent variable and one or more independent variable by fitting a linear equation to the observed data set. So now look at this. We have these blue dots are different data we have. So what we are trying to, our main focus on linear regression is to just get the line of best fit, right? So now with this line of best fit, we can predict values. So for example, say this is room numbers, right? So let's say these are room numbers 10, 20, 30, 40, 50. And now this is the price of the particular house. So if your room number is say 10, if you draw a dotted line up to this best line of best fit, then we trace it to this y-axis, then it will give us the price that house will sell for. So it could be anything, basically. It could be anything. It could not be room number. It could be how many hours of sleep do you get and how happy are you, happiness index. It could be anything, basically. It could be two values you're trying to like plot. So now what linear regression will just do is it will fit a straight line. Now we have a dependent variable and we have an independent variable, or we have one dependent variable and we have multi independent variables. But for this class, we'll be talking about a very simple form of regression, which is which is simple linear regression. We'll be using just one dependent variable and one independent variable to get our line of best fit and to make predictions. So one thing I feel people that teach machine learning don't talk about is inference. So the aim of when you ask people what is your aim of machine learning, their aim is basically to predict, right? They just want to make predictions. Oh, if I have this, if I have this, what would the outcome look like? What would the output look like? So basically, the aim of machine learning is not just prediction. We are not just predicting when we are doing machine learning. We are also trying to make inference. So now the inferential thing about it is that we can so we can estimate the effect of the independent variable on the dependent variable. So what I mean by that is how will the independent variable affect the dependent variable? If I change the independent variable by say 5 units, what would happen to the dependent variable? So we're not really concerned about just predicting the values of the dependent variable. We are also trying to like see, okay, so if I spend 1,000 more on marketing, what would happen to our revenue? If I spend $1,000 less or $1,000 less on our marketing, what would actually happen to our revenue? So basically, you're trying to make inference, right? You're not just trying to predict that, oh, if I do this, this is what is going to happen. You understand? So we're also trying to make inferences from our data sets and not just predict alone. So basically, that is the aim of linear regression. So now we'll be talking about simple linear regression. And I mean, if you've not been paying all of your attention so far, I would actually appreciate it if you pay a lot of your attention, because we'll be doing a little bit of maths just to simplify, just to simplify what we have for this class. So again, if you're not very good with maths, don't worry, we'll make it as simple as possible. So simple linear regression, and we'll be wrapping up probably in 30 minutes. So again, thank you for your time and staying tuned. So simple linear regression is a model that basically describes the relationship between, I told you the fact that it has this simple in its name, right? So the simple is trying to say we are just dealing with one independent variable and one dependent variable. So we are trying to model the relationship between the independent variable and the independent variable using a straight line. So this is a straightforward approach for predicting y using x. So you might see different books or different tutorials call the independent variable and the dependent variable with different names, right? So for this course, we'll be sticking with dependent variable as y, independent variable as x. Some people use response, they're just different things they use. So just to simplify, just to make it simple, we'll be using y as dependent variable and x as independent variable. So mathematically, to model the relationship, we say y, right? Y is the continuous function, right? So y is equals to beta naught plus beta 1x. Now, beta 1, this beta 1 we have here, is basically the gradient of that straight line, and beta naught is basically the y-intercept. So an x we have here, x is the independent variable. So depending on our data set, x can be the room number, x can be age, x can be the amount of time you sleep, and what have you. So now to fit this straight line, the most common approach to fit this straight line is using least square method. So some people call it ordinary least square. So basically what least square is doing, and please we'll be going to calculations just very soon. So what least square is doing is that it is just trying to find that line of best fit, right? It's trying to find that line of best fit between our data. So now the technique of least square, it generates some errors. Even the fact that it's trying to like find that line of best fits, we have some errors. So now if you look at these data points, right, these are like different data points we have. Sorry, I just want to admit this person. All right, so we have different data points, right? So these are the different data points we have. So now the line of best fits we have is just passing through just one point. So now every other point this line of best fits is not passing through. There are some errors that are generated. Now we try to minimize this error using this least square approach. So now from this point to this particular line, these dotted lines, they are basically errors. They are basically errors. So remember we said to predict, we use a particular function, and the function is this is the particular function, right? So now with this ordinary least square line, with this line of best fit, it is also generated using a similar function. This line also has a function, right? So now, but every value we get with this line, they are called estimated values. They are not the actual values, right? They are the estimated values. So we represent them with y cap, right, or y hat. Now these particular values, right, we also got them with that same equation, right? So now the distance from the original, the distance from the actual value to the estimated value are called residuals. Some texts will call them errors, right? E or residuals. So now to get this, to get this mathematically, we represent that residual is equal to like the actual value, right, minus the estimated value. So that is how we get the residuals. So basically what least square is trying to do is that it's trying to like fit the best fit line with the from the set of points, and while it's trying to fit that line, it is also trying to minimize error. So in this technique, the sum of the square of the offsets, which are the residuals, are used to estimate the best fit line instead of using like the absolute values. So if we are using the absolute values to fit the line, it will be overfitting because we cannot get a single straight line to like fit all of these data. So now let us just do a little bit of math. But before we do a little bit of math, let me just explain the residual further to you. So in the previous slide, I said the residual is given by this formula, the actual y minus the estimated y. So to cater for the negative values, we square the residuals. Would understand this when we get to the mathematical part. So it's fine if you don't understand it right now. So now we use this method called the residual sum of squares. So you see it as RSS. So what RSS does is, and why we are basically squaring it is that some of these values are above the estimated line, and some are below it. So some values are negative, some values are positive. So to cater for that effect of negative and positive, so basically that is why we square. So now once you square, so now we have the residual sum of square as the summation of all of these errors, right? All of these residuals, e square, the first error to like the last error. So now, and we have to recall, right, that the formula, right, that function is given by this equation, and now this is e is equals to y minus y cap. So if you substitute this e into this formula, and you also substitute this y into this y cap, you get this formula. So this equation, the first error, the square, this squares of errors, the e1 square, e2 square to en square, it basically becomes this if you substitute all of these values into this equation. So you have this. It's fine if you don't understand what I'm talking about. We'll do it mathematically very, very soon. So now the formula for the residual sum of squares is this. So now from the least square approach, basically what it's trying to do is that we're trying to minimize this error. We're trying to make this error as small as possible. So once we get this error, like once we get the minimum error for RSS, it draws this best line fit for us. So now once we have that best line fit, we can now get the values of beta naught and beta 1 mathematically. So mathematically, we have to differentiate. I mean, and that is a lot of math which I don't want us to go through. So we have to differentiate we have to differentiate this RSS. So if you differentiate this RSS, we'll differentiate with respect to beta naught, and we also differentiate with respect to beta 1. We get the formula for beta 1 as this, and get the formula for beta naught as this. So all what I've said might have been very, very abstract. You might not even understand. It's fine. So now I'll just use so I when I was preparing this slide, I intended to use Microsoft Paint to illustrate, so we'll get everything I've been trying to explain so far. So I just figured instead of using Microsoft Paint to illustrate, I could actually use Excel as well to illustrate. So let us use Excel to illustrate. So just to make things better for us. So now let us have and also have like our independent variable. So we call remember our independent variable. Our independent variable is our x. So let me just have it as var, and this is our x. So let us give our independent variable some random values. So let's say 1 to 5. So let's just give it 1 to 5. And all right. So also now for our dependent variable. So our dependent variable is our y. So let's give our dependent variable random numbers too. So let's say this is 2, this is 4, this is 5, this is 4, and this is 5. All right. So now this is our dependent variable. This is our x and y. So what we can do is to just have a simple plot. So if you have a simple plot of this, can have a simple plot. So if you have a simple plot, so this is what our plot looks like. So we have x and we have y. So this is what it looks like. So this is just trying to so what I'm trying to do now is trying to explain everything I've done here mathematically. You know, here we're just talking about formulas and stuff like that. So let's just explain them mathematically. So now we have our x and we have our y. So this is our y and this is our x. So if you plot now, looking at this, when x is 1, y is 2. So when x is 1, y is 2. So we have this first plot. So if you do that for every other thing, we have this plot, right? So now we have to get the mean. We have to get the mean of x and we have to get the mean of y. So to get the mean of the values in Excel, we use the formula average. So now, average of all of these values. So now the average of all of these values is 3. Now again, let me just paint this so we understand this is the average. So again, we do the average of the dependent variable. So we use the same formula again. So we say equals to we say average. So so average of the dependent variable, which is y. So now this average is 4. Just hold on, I want to admit someone. All right, so the average of this value is 4. So after taking the average of the dependent and the independent variable, so now what we need to do, remember I was speaking about residuals, right? I was speaking about residuals when we were talking about this. So now the residual is just the difference from this actual value to the estimated value, and this estimated value is the value we got from the mean. So now if you look at this value, right, we have x as 3 and y as 4. So now if we're trying to draw our regression line, that straight line, if we're trying to draw this line, if we're trying to draw this line of best fit, it must pass through 3 and 4. So because this is our mean, right? This is our mean of the dependent and independent variable. So that means that value must pass through this point. It must pass through this point 4. This point, right? It must pass through this point, that line of best fit. So now, if the line of best fit fits, okay, so let me just copy this. Let me copy this, and I think I still have to use the paint. All right. Just to illustrate better. So what I'm trying to say is that line of best fit, right? you remember the x, the mean of x was 3 and the mean of y was 4. So that means the line of best fit must pass through this point. It must pass through this point. So the line of best fit is something like this. Pardon, my line is not so straight, but that line of best fit must pass through this point. Now for the residuals, now the residual will be this actual value to this predicted value. Now this actual value to this predicted value, this actual value to this predicted value, the actual value to this predicted value, the actual value to this predicted value. So that is basically what we are trying to do to get the residual. So to do that, what we have to do is so we say x. So we have this x minus mean of x. I'm trying to get that mean of x. So mean of x is meant to be something like bar x. So that's what I'm trying to get. So let me just copy it from. Let me just copy it. Sorry. So now this is the residual. So basically, what we are trying to do is x, right? This x. So we'll just say this is equals to x, right? Let's put it in brackets. Sorry about that. So x minus now the mean of x. So if you do this, this is the residual, right? Now remember I was saying we have to square it just to cater for the negative values. So this is what I meant by that. So now let us just have this for all of the values. So this is what we have for all of the values, right? So now the rule of thumb is, okay, the equation is wrong. So I think I have to do it manually. That didn't work. Sorry, just hold on and stay with me, right? So again, we have to do x again. So we have to do x minus now the mean of x again. So if we do that, we get minus 1. So we do the same thing again. We say x again. So this is 4 minus the mean. So what I'm trying to do here is just basically trying to get the residuals, just the residuals. So we do this for, I skip this row. So we say 3 minus the mean. So we do that. And also finally, we have this. So we say x again minus the mean. So we do this. So normally the rule of thumb is if you sum up all of these values, the residual should always give you 0. It should always give you 0. So if you sum all of this up, it should give you 0. So now to cater for, like I mentioned earlier, to cater for the negative sign, so we have to square. We have to square all of these values. But before we square these values, let us also do let us also have y. So now what we've done is we've gotten the residual for the x values, right? So we have to get the residuals for the y values as well. So let me just go back to paint and make you understand something. So now we have these values, right? We have these values. Let's say this is for 3, right? This is for the x-axis where we have 3. So what we've done so far is we've gotten these residuals, right? We've gotten these residuals. We've gotten the residuals for x, right? So now what we want to do is also get the residuals for y. And now to get the residuals for y, remember y is 4, right? So y is just a straight line like this. So we have to get all of these residuals as well. We have to get all of these residuals as well. We have to get all of these residuals as well. So now to do that, we have to do y again. So y minus let me copy the formula for y. Okay. So y minus the mean of y again. So we have to do that. So we say equals to, now we say y. What is the value of y? 2 minus the mean. So we say this. So these are the residuals for the y. So we do this again. We say equals to, say 4 again minus the mean. 4 minus 4, that should be 0. So now the next thing for the value, we say 5 again. So we say equals to, so we say 5 minus, now we come here again to the mean. And also for this, we say 4 minus 4. That's the mean, so that should give us 0. And finally, for this particular value, the y is 5, so we say 5 minus the mean. So now, like I said earlier, all the residuals, right? When you sum all the residuals up, it should give you 0. That is how you should know you are doing the right thing. So this is 2 minus 2, so it should give you 0. So that means you know you are actually doing the right thing. So now, to cater for all of these negative values, right? So what we have to do is to like square all of this. So that is why we from here. Remember we said we have to from here. Remember we said we have to square this, which gives us the residual sum of squares, right? So now we go back to Excel and we square this value. So now once you go back to Excel, so I'll just paste this and I'll give this square. So just permits me using the symbols. So now what we want to do is to square these values, right? So now we'll say this is equals to so now this is 4. So let's just do the same thing for all other values. So now once we've done this, we also have to square y. We also have to square the residuals for y. So if we put this, and I'll just say times 2. So we say this is equals to, now if you notice, while we're squaring the residuals, it has actually catered, that's catered for all of the negative values. Now squaring them caters for the negative values. So we say this times itself. We say enter. So now we do the same thing for all of the other values. So now we have this. The final thing we need to do to obtain beta naught, which is the intercept, and beta 1, which is the gradient. So we have to multiply these two values, this particular value and this particular value together. So now if we do that, let me just copy this. Excel is not permitting me to copy that and paste it, but what we need to do is to multiply these two columns together, okay, let me just write it out, maybe that'll be better. All right, so now we just said this is equals to this multiplied by this, and we'll get our answer. So we do the same thing for every other value. So we have this. So now we need to sum the residuals. So if you sum the residuals, so we just say equals to, now you say sum. So now we need to sum all of the residuals. So if you sum all of this, we need to sum the residual squares rather. So if you do that, you get 10. So let me just print this 10 as well. So you get 10, and also for this we need to also sum all of these values. So now if we say sum, now we are summing all of these values, so we get 6, right? So let me just paint this. So now this what we've done here is what I've been trying to explain using all of this. So now we are trying to get beta 1 and beta naught. So now to get beta 1, what we need to do is to divide. What we need to do is to divide 6. So we say beta 1. So let me just do b1, and now that will be equals to what we have here, this particular value, right? So it is equals to this particular value 6 divided by this particular value. So that is beta 1. So beta 1 is 0.6, right? And now beta naught is the intercept, right? So let's say beta 0. So now to get beta naught, so now mathematically, if you look at this, let me just share my slide on my screen into 2. So if you look at this formula, right, this formula for beta 1. So this formula for beta 1 is saying the summation of the residuals, right? So, and that is what we've done here, and you divide it by this particular value. So what we did so far is to sum these two values together, right? Which is this, and we divided it by this particular value. So that is how we get beta 1, right? So that is the back end. This is what our computer is doing in the back end when we start coding tomorrow. So today we are not coding, we're just using Excel to explain. So now the beta notes now. So far we know that the formula to get y is equals to the formula to get the estimated y is beta naught plus beta 1x. So now um, we have our values already. So what we need to do is just tweak this formula and make beta 1 the subject of formula. So once we make beta 1 the subject of formula, once we make beta naught the subject of formula, we'll be able to like estimate our y. And to do that, what we just need to do is the y at minus beta 1 times the mean. So to do that, what we need to do is to say, all right, so let me just go back to this page real quick. So remember that our values for y is 4. When we did the mean, the value for y was 4 and the value for x was 3, right? So now what we have to do is to say, we just slot into this equation, we slot for our y, for the estimated y, we slot 4 here, and for the estimated x, we slot the mean of x, which is what we got here, 3. So you slot this 3 and 4, you slot this 3 and 4, so you slot this 3 and 4 into the estimated y cap, and you also slot it into the estimated mean. And now we have our beta 1 at 0.6. So if you do that, so now if you follow this particular formula, so beta naught would be equals to, so we just say equals to, now we have our y cap is 4, so we just say 4. Now we have to minus 4 minus beta 1, beta 1 we got at 0.6. So we say 0.6, and now you have to multiply 0.6 by the mean, which is this 3. So we say 3, and we enter. So now our beta naught is 2.2. So all of this is to just show you what is happening in the background. We don't need to do this. I'm just trying to explain how we derive the formula and what is happening in the background. So at the end of the day, you can actually, Excel gives you an automated way to do everything I've been doing so far. So on your Excel, you just click on this plus icon, and now you can draw the thread line. So now if you look at the thread line, right, you'd see this thread line is passing through this 3 and this 4. So this is the regression line for this data set, for this independent and dependent variable we have. The thread line is passing through this mean we got. Remember, we got this mean 3 and 4, right? So it is passing through on the x-axis, it's passing through 3, on the y-axis, it's passing through 4. So now, based on the residuals and everything we've calculated so far, now we can also get beta 1 and beta naught. So to do that again with Excel, you just come to this plus, and you come to more options for a thread line. So once you get to more options, now we are dealing with linear, right? So that's why linear is on. Now you can use any of this other method, but we'll not be talking about other methods because we are basically focused on linear regression. So now we want to get the intercept. Sorry, we want to get the equation here. We want to get the equation. So now to estimate any value of y, the equation now becomes, remember we had this equation, right? Y, this equation here. We have. Let me just copy this. Sorry. This particular equation, the estimated value of y is this. So let me just copy this, right? And now going back to our Excel, so we have this as our so this is the formula of our estimated y, right? So now y is equals to beta naught. Now we've got beta naught as 2.2, right? So now this is just saying y is equals to 2.2 plus beta 1, 0.6 x. So to get the value of, to get any estimated value, so what you have to do to get x can be 1, 2, 3, 4, 5, 6, and what have you. So to get the estimated value of, to predict y, you just have to slot this formula, right? You have to slot this formula and you have to put your x. So basically that is how you get regression line using Excel and mathematics and all of this. So I'm just trying to show you how we do that on Excel. So I think there's one more thing I want to show us. Okay, so now the R square value. We'll talk about that. We'll talk about that in a bit. Let me just switch off the. My Excel is not responding, so I want to switch off. I want to switch this off and display the R square value. Okay, let me just leave this and not waste our time. So basically, what I've done on Excel, right? I think I've added one person. So basically, what I've done on Excel is trying to show us how to get all of these residuals, how to get the equation, how to get the y-intercept, and that is how we do all of this in Excel. But tomorrow, when we are doing this, we'll be doing this using Python. So we don't even need to so you don't even need to remember all of this thing I've said so far. If it's feeling, if it is vague at the moment to you, if you don't understand what I've said so far. So now, how do we assess the accuracy? How do we assess the accuracy of what we've done so far? So there are two ways we assess accuracy. So we assess accuracy of the predicted coefficients. So now the predicted coefficients are those parameters, beta naught and beta 1. So how do we trust these values are actually correct? We can actually trust the predicted values. So to do that, we use something called the p-value. We discuss more on this tomorrow. So the p-value is basically a threshold, right? So you set a threshold for your p-value. So if the p-value is less than a particular threshold, usually 0 0.1, then you say it passes, and you can actually use that p-value. Now, how do we also assess the model we've built? How do we assess that accuracy? How do we trust that this model we've built can actually predict correctly? So we use the R squared method. We use the R squared. So basically, to get the R squared is just to, if I go back to Excel, is to like impute this formula in Excel and calculate the R squared. But instead of imputing the formula in Excel, we can just automatically we can automatically display the R squared value. So now the R squared value is 0 0.6. So I don't want to go into the mathematics to prove this. So we won't like just borrows, but the formula, this is the formula. So you can just try this on your own. So if you input this formula, you get the R squared value. Now the R squared we got for this linear regression we did is 0 0.6. So that's just how certain we are what we are doing is correct. So R square value basically ranges between 0 to 1. So now if R square value was 1, that means all of these points we have, all of these points would actually be exactly on this regression line we fitted to our data set. So that is how we get R square. So R square basically it tells us so the R square value tells us how well that regression line predicts or estimates our actual values. And like I mentioned earlier, R square ranges from 0 to 1. So the closer it is to 0, the better our model. So what we had there was 0 0.6. It's not bad. It could be improved, but we'll talk about all of that tomorrow. So basically, accuracy assessment is where we'll be ending today's class. And tomorrow we'll be talking. So tomorrow, basically, we would move, would we'll stop using Excel and we'll like use Python, and we'll talk about how we could do everything we've done on Excel within everything we did in Excel now took us maybe 10 minutes or more. But with Python, in a minute, we'll just write a few lines of code and we'll get what we need. So tomorrow we'll be talking about today we've spoken about linear regression. So tomorrow we'll be talking about data processing, understanding the business problem. We'll also be doing EDA and future engineering. We'll also be visualizing our data. Then finally, we'll implement linear regression. So tomorrow we'll talk about all of this. So that will be a wrap for today's class. I thank you and I appreciate you for your time for sticking with us. So if you have questions, now it's time to entertain questions. Now it's time to entertain questions. Please, if you have questions, feel free to go ahead and ask your questions. But before we leave, please, before we leave the class, I would like us to turn on our cameras. Let me just stop sharing for a moment so we can turn on our cameras. And um, the last class, I didn't remember to take pictures of the class. So please turn on your cameras and let us just do one or two quick pictures, please. So you can also go ahead and ask any questions you have about the class, what we've discussed so far. Any questions? Yes, thank you for that question. And asking that question makes me remember what I wanted to tell us about if you're a beginner with Python, right? Because tomorrow is basically Python. We're doing Python tomorrow. So if you're a beginner with Python, please go to our YouTube channel. We upload our videos about an hour to 2 hours immediately after the class. So our YouTube channel is the Geospatial Hub. So kindly subscribe to the YouTube channel. So within an hour or two, the video will be uploaded on YouTube. But please ensure you like subscribe to our channel, follow us on all our social media platforms. Then tomorrow, basically Python. So please come watch this Python walkthrough before tomorrow. Watch this Python walkthrough so you won't be naive to whatever we are trying to like discuss tomorrow. So I hope that answers your question, please. Please, has anyone been able to take a screenshot of everybody in the class, please? I'm struggling to do that. I can't change my layout. Yeah, I would appreciate it if you send it to me, the screenshots, so we'll just be able to post it on our social media. So I'll just leave you my email address. All right, so I left my email address in the chat box. So you've been able to like take a screenshot of the old layouts of everyone. I would appreciate it if you send it to my email. I would really do appreciate it. And any other questions? So let me just go back sharing my screen. So if you have questions regarding what we've done so far. So just to like give a brief recap, we started with this. So the class was basically about introduction to machine learning. We spoke about the hub. The hub is just to what we do at the hub is to bridge the knowledge and skill gap found in geospatial professionals, and we're trying to just do these webinars and courses, and just to like give these job professionals the skills they need to meet up with international standards. And also, we spoke about our website. We'll be launching our website 9th of this month, and this is just a little bit about me. And from the form responses, we got a lot of people with 40% of the audience are beginners with Python. So this 40%, I recommend you go to our YouTube channel and watch our YouTube videos on Python. So this is the content of what we discussed today. So today we discussed the basics of statistics. We discussed the type of data we have. We discussed the quantitative and the qualitative. We also further discussed the quantitative and qualitative into discrete, continuous, nominal, ordinal, and we talked about the type of statistics, how we can measure center, dispersion, and also inferential statistics and all of that. We talked about the relationship between mean, median, and mode. We also spoke about how to measure dispersion. Then we started with machine learning. We went to talk about supervised and unsupervised learning. We talked about classification and regression under supervised learning. And we also spoke about linear regression, which is our main aim for this class. So tomorrow we'll be doing linear regression with a whole lot of data sets. Like, trust me, it's going to be an awesome session. So tomorrow is not theoretical. Today was just basically theoretical. Tomorrow we're going to practicalize every theory we've put in place today. So that's a wrap for today's class, and I would like to entertain questions before we wrap up by 12. All right, so if there are no questions for now, come prepared tomorrow with your questions, and thank you all. That will be all for this.